Yeah, so I wanted to tell you about memory management and how that works. If you started out with a language like JavaScript or Java or C Sharp, then you're using a programming language that has automatic memory management. And specifically, those languages use a garbage collector, which is a invention that came about at some point. A lot of that work was done in the self programming language, which is related to the Smalltalk programming language. But before we had that, like an older programming language like C, developers had to manage memory themselves. And I kind of first want to lay out how that would work to give an outline of some of the things I wanted to cover. First, manual memory management, just a little bit. And all of these are not going to be very in-depth because we don't have that much time to go into it. If you want to learn more about it, you can read up on it more. There's two main categories of automatic management. One is called garbage collection, and then the second one is called automatic reference counting. I would say this is maybe too specific. I'm gonna call this just reference counting. Within this reference counting scheme, there's multiple ways of applying this. I don't even know if I want to call this reference counting. Maybe like I'm gonna actually call this scope-based automatic cleanup. But the main one I'm gonna focus on is automatic reference counting because that's the one that I've studied the most.
Gotcha.
Okay, so let's first talk about manual memory management. This is a hello world in C. First of all, there's two ways in which programs use memory. One is the stack, and the second way is the heap. The stack is used for local variables that are needed within a function. So if you have a function f and it takes parameters x and y, I don't know, it declares more variables in there. The stack is responsible for allocating space to hold all of the local variables, including the function parameters, in a frame of the stack. If at any point in time the program decides to call this function f, stack means it's a first in, first out data structure. So if we call this function, we put this stack in here, and it'll remember like that. Well, this you called me, and then I'm gonna initialize the values of x and y. And when it encounters this line, it'll also initialize the value of a, and so forth. So all of this information is remembered for the purpose of executing this function. If sometime later inside the body of f, if f decides to call another function, say g, we will push another frame onto the stack. This is called a frame. This rectangle here is called a frame. So we'll add an additional frame for the purpose of whatever g needs to remember, right? And maybe, I don't know, g has a w variable. I don't know. So this is how it works. And when g finishes, when the execution of g is done, then this frame can be destroyed. And then we're left with just the f frame and so forth. So this is the stack memory, and that's not what we're going to talk about, although we just did, but not in depth. The heap memory. Now, the one thing about the stack is that you can see that the things gets destroyed on the fly and get created on the fly as functions are called and end, right? Everything that's remembered on the stack is short-lived. So the stack is not going to work for long-lived objects that you need to remember. So long-lived objects is what the heap is for. Such as like there's some array data structures or dictionary data structures that you want to remember across all of these function calls. You don't want them to get destroyed just because the function is finished, because you might want to pass that on to another function that needs to work on it, etc. I don't know why they called it the heap, but they do. So let's call it the heap. But other names for the heap might be dynamic memory. Yeah, so an example of using the heap would be, I have a function, maybe. Inside this function, I'm gonna make an array. This array is gonna contain these two numbers that got passed in. And then I'm gonna pass this array to G. There should be an equal sign in here, sorry. So if we did this, like this is the stack. So we first will, like, somebody has to call f first. So when you call f like this, we're gonna make a frame on the stack for f, and we'll have a is 2 and b is 3. We're gonna make an array variable now, and the content of the array will actually point to the heap. We're gonna allocate an array on the heap, and we're going to place the numbers 2 and 3 inside the array. And
so the heap is not like specific to this frame or to the stack, right? It's
correct.
Just somewhere that is dependent.
Yeah,
gotcha.
That's why it's called long-term memory. It will live on. It will live on even if this stack gets cleared out.
Gotcha.
So now this array variable is going to be a pointer that is referencing this object, and there's an address where this actual data is stored in the heap. And now if we call G, we'll add another frame into G. Well, we're actually passing to G this array variable, and maybe G has its own name for this array. I don't know, my array, and this my array is gonna point to the exact same object in the heap. And when G is terminated, then this frame will go away, but this array object will not go away. When F goes away, do you think this object will go away?
No, it will still be there, right?
Depends.
Okay.
Well, I'm writing pseudocode here, so you don't know what language I'm using. But it depends on what the language does. If it's JavaScript or Python, then this array will go away because memory is automatically managed for you. And it can see that there's no one else that could possibly would want anything to do with this array anymore, because this array was created within the body of F, and F hasn't handed this to any other place that could be active. It handed it to G, but G is dead now. And it didn't return the array to anywhere else. If it had returned the array, that's a different story. Then you have to worry about, maybe we need to keep this array around, but that's not the case.
So it basically keeps like a registry of who is going to potentially use the array.
Yes.
And if they're like, okay, nobody's going to use it, then I'm going to automatically destroy it in the language that you don't have to worry about it.
Yeah, and the behavior I just talked about is the garbage collection and also the ARC. Both of these systems will do that for you. Will automatically clean up. But if you're using a programming language like C, then it will not do that for you. And I'll show you maybe a little bit of code. Let's say you have, let's not do structs. Let's just do array. Now in C, it is actually possible to create an array in the stack frame memory, by the way.
Okay.
It's possible to do that, although we're not doing that here. C gives you the option of, like, if you write it in a certain syntax, numbers. I think this is how you do it in C. This is an array of numbers. And if you had written it in this syntax, that means the array of numbers actually goes on the frame. So this is not a use of dynamic memory. C gives you the choice to do either way. But
Gotcha.
We're not going to talk about that. We're going to talk about dynamic memory. I want to store this array in the heap. How do I do that?
Okay.
I need to ask the C standard library to allocate some memory, and the function we use is malloc, which stands for memory allocation. So we're gonna malloc. So if you hear the word malloc anywhere, that's what that means. It means memory allocate. So this is the API docs for the functions in the standard lib library, and one of them is malloc. Malloc takes in one parameter, which is the size. It wants you to tell it the number of bytes you want to allocate.
So does it have to do with how many or what is the information you store in the array?
Yeah, so like if you put in 12, then that means I want 12 bytes. But like as a C programmer, how do you know what kind of data structure requires how many bytes to store, right?
Right, exactly.
C does give you a method of calculating that for you, and that method is size of. If I have an integer array that has two numbers in it, I'm gonna try this, see if this works.
Okay.
No, I'm gonna get the size first before I ask for the memory. So print a number. This is how you do it in C, and then I'm gonna call this f function here. So I'm gonna gcc compile this file, and I'm gonna say output the resulting binary as mem.bin, and then I'm gonna call mem.bin. The size is 8. So apparently if I want an integer containing two numbers, that is gonna cost me 8 bytes to store the information in that array. 8 bytes of memory. And if I wanted to store 10 numbers, I would guess that would be 40, right?
Okay.
Just based on doing some math, yeah. If I wanted to integer type in C, that's gonna cost me 4 bytes. And an array of that is the number of elements times that number. Okay, so anyway, so now that I know the size, the number of bytes I'm gonna need to ask for, I'm gonna call malloc and ask for that size. And then I'm gonna receive it. The type of the receiving value, an initializer. Okay, so it won't let me do this because there might be a way of writing it in this syntax, but I think more or less it's telling me if you're trying to declare this as an array, then you're gonna need to figure out more specifics about the array, which I don't care to give because this is coming from dynamic memory. It's very dynamic. So what I'm gonna do instead is call this is an integer pointer. I'm gonna make this a pointer, and in reality, anything that malloc returns to you is a pointer to some place in the memory. And pointer is a concept that newer languages don't have. It's a lower level concept. Essentially, it's a memory address, and it represents a reference to some dynamic object, either in the heap or on the stack. So I believe this will at least compile. Yes. I basically took the value that malloc returned to me, which is a pointer, and I said I'm gonna assign it to a variable which is an integer pointer, which can be used to represent an integer array. And then after that, I can start like utilizing this. I can say the first number is 4, the second number is 19, and so forth. And I have to remember the length of the array myself though. So let me make sure I remember that. So now I can do something like for I plus 1 times 2. I will just initialize this array with something, and then we can maybe even return it out. We're gonna return this array of numbers which was allocated on the heap back to the outside, back to the caller. And then maybe we'll loop through it and print it out on the outside to prove that it worked. Okay, we'll just hard code the length for now. But this time I'm not gonna assign to it, I'm gonna print it out. It's printf, not print. Okay, that actually compiled. Yeah, okay. Let me put a new line character here so that it's separated. Yep, so that worked.
So what if you go over the allocated memory?
Great question. Let's try it. Oh. I'm so glad you asked that question because do you see what's happening here?
Yeah. What did you do? Why it prints this stuff?
I artificially changed the length it thinks it is to 20 instead of 10. Even though only 10 was allocated, once it returned back to the caller pretend it had 20 elements in it.
Right.
So what do you think is going on here?
Not sure. Wait, where do they get these numbers from? Does it point to some other memory location to get these numbers?
Yeah. So actually what happens is it's extremely hilarious. Well, the heap is just a large section of memory, right? I think a memory chip looks like this, and then you slot it. There's this slot. You push it into the slot. Like a game cartridge or something like that. There's these cells inside, like basically there's a lot of, you can just think of it like a mailbox, a lot of mailboxes right next to each other. Like it's arranged like a grid, and all the grids are numbered 1, 2, 3. Every address space is numbered. When we ask malloc for some space, some of these will already been allocated because somebody else malloced for it. Somebody is using this already, so you can't use that. When you call malloc is like, oh, I found this one, you can use this one. So I'm gonna return 6 to you. So the thing in here is actually the address 6. I'll put a star next to it to mean this is a 6 address, is pointing to here. So malloc actually returns a number back because pointers are just numbers, which are, everything in computers are numbers. I don't know if you know this.
Yeah.
Everything in computer.
So when you have the size, does it still only return like one number, or it will give you like a consecutive like series of numbers in this case?
Yeah. So actually, the way that works happens later, actually.
Okay.
Which is important to understand. So malloc is like, yeah, okay, because they wanted 10 boxes, let's say.
Right.
I'm gonna assign 10 boxes starting at 6.
Okay.
To your program. So that's yours now. Okay. This chunk is mine to store my numbers, and malloc just returned me the address of 6. I'm thinking this is an integer array. In reality, it's just the number 6.
Gotcha.
I'm gonna prove that to you by just printing out the memory address as a number. So you can actually print that out. Okay. Why is this still negative? I'm not sure why, but it's okay. We don't have to dwell too much on it. But essentially what I'm trying to show is that this is a address number that's similar to my table, right? They just have a much larger table than I do, and so this array is nothing more than an address into this table. And then the way your program then accesses all the numbers in the array is actually by adding an offset to this number.
Okay, gotcha.
So like you gave me 6. So in order to access the 0th element, well, that's 6. In order to access the first element of the array, that's 6 plus 1.
Right.
and so forth, right?
Okay, so it just gets into the location after what you got.
Yes.
Actually.
Yeah. That's called pointer arithmetic. That you're just adding and subtracting offset numbers from one address location to get another. The C compiler, when it looks at this array indexing operation, it will do that arithmetic automatically for you.
Gotcha.
Because like this number, let's say I is 4, and it sees that you're trying to access index 4 of this got numbers array, and it looks at the type of got numbers and says, oh, it's a pointer to an integer. It's trying to be used as an integer array. Let me figure out the size of an integer. An integer has 4 bytes. Every integer is 4 bytes. So when you index into, so when you do this, I'm gonna do I. So I is 4. So if I'm trying to index into index 4 of this array, I'm gonna do 4 times the size of integer, which is 4.
Right.
We end up with 16. Well, okay, so there's actually 4 boxes if we're gonna do it like that. For every number, we need 4 bytes.
Right.
Okay, and so forth. So the 16 is like, I need to move 16 over to get to this element, which would be at index 4. It's the beginning of here, actually. So this expression, what it actually does is 6 plus 16 to find the memory location of here.
Right.
And then it retrieves the value from that memory location. It retrieves 4 bytes to make a number from that memory location. There's an operator in C that actually does this explicitly, even though this one does it implicitly for you. You could do this explicitly yourself using this star operator. Star operator says, given a memory address, go there and fetch the number. And then the result here is the number that's in the memory location.
Question. So how does it know it needs to grab the next 4 bytes there?
It knows because this is a strongly typed programming language, and all variables are tagged with a type identifier.
Gotcha.
Now, in JavaScript, obviously they would have to do it differently. Well, you don't do the memory handling of this stuff in JavaScript anyway, so you just don't have to do it. JavaScript does it for you.
Will JavaScript figure out how to allocate memory yourself? I mean, I guess you don't tell it the size.
You don't tell the size. The arrays are dynamically sized, and it'll just ask for more as you need more memory. Like if you dynamically push elements to an array, then it's gonna realize, oh shit, I need more memory, and then go ask for more if needed.
Gotcha.
So, but all of this, I was basically trying to answer your question of why we got these extra weird numbers back here. Can you answer that question now?
Yeah, I think it's just keep going down.
It's whatever junk is in here. It also printed out, even though that doesn't belong to you. You're still accessing it, which shows a huge problem with this design, which is that you can access data that does not belong to you.
Right.
And that's actually a source of a lot of security problems, because when programmers make bugs in C, they can actually, hackers can actually take advantage of that. And if it's a network program, let's say you're a website that allows people to upload images or something, and then as one of the parameters is you're gonna tell me how many bytes are in that image, and if the hacker gives a fake number for that length, and it tells your program a bigger length than the actual images, it could actually end up causing the program to read data from a different part of the program. And that different part of the program might be some other information that the program is remembering, and maybe the hacker can figure out a way to access that data that the hacker should not have access to.
So why C language is designed this way, to have you at least have the ability to access the memory location directly?
Well, mostly it's historical, right? Because back then people haven't come up with automatic memory management schemes yet. So that just wasn't available. They were dealing with very primitive tools. C was already a huge step up. Like it was already a huge improvement versus assembly language programming. Right? There was a point in time where you didn't even have C. This was the only thing they knew how to do back then.
Gotcha.
Right? But having said that, though, there are advantages to having this level of access, because like copying memory is one of the performance intensive things you can do with a program. Like when your program is slow, oftentimes is because it's accessing memory in a poor way. And when you have a low level of control like this, you can come up with hacks that makes your program much, much faster, because you can smartly access the memory. And instead of copying stuff 2, 3, 4 times, sometimes you can just smartly do everything in one pass and only have to copy things one time.
So basically it's good for like a machine that has very limited memory.
Yes,
so that you can...
exactly. Such as cell phones. Although cell phones are, very powerful now, but it's not always that way. So it definitely helps in embedded devices, which is why when you write a iPhone app, for example, the Apple team still not willing to go to something like JavaScript or Java. They still want to go low level. At first they have Objective-C, and now they have Swift. Swift uses a memory management scheme called ARC, which again stands for automatic reference counting. And Objective-C, in the old days, everybody who wanted to make an iPhone app had to use Objective-C, even though it's a terrible programming language, in my opinion. But this is like a semi-automatic ARC is how I would characterize that. I don't think we have time to talk about garbage collection or ARC, so maybe we can save it for next time. But I do want to finish this discussion about memory management. We can't end until we talk about how do you free the memory that you've allocated already.
Oh, that's true. Can you just override it? Why freeing it is necessary? Can you just later just override?
Yeah.
So that you don't have...
Well, in terms of this analogy of the registry, like if I allocated a block of memory to you, the purpose of free is to later on just yield it to other programs or other parts of the program who might need to use memories. Like, I'm not using this anymore. You can mark that as unused so that other programs that do malloc later, they can access that one. Why would you want to use free? Well, if you continue to only allocate and not free, the system might not have enough memory resources. Usually a system that doesn't process a large amount of data will never have a problem. When your program completes, all the memory is going to get freed anyway. So that's not a problem. It's only when your program is kind of long running, and also it has to go through a lot of data or generate a lot of data. And then that could become an issue. You're going to end up mallocing for a lot of memory, and if that keeps piling up without freeing, you might run out of memory. The way you free something, I think it's just free. Let me make sure. Yes, it's just free. We don't get any indication though that it worked. So I kind of just have to trust that it got freed.
Can you print the thing like the same value of the memory location?
Yeah.
So after freed.
Okay, I will. I think it'll still print it.
Okay.
Yeah, it didn't change. The reason is, first of all, I don't have any code. Clearly, it's gonna stay the same because I didn't reassign a value to got numbers. I only passed it to another function, and that function has no way of modifying my local variable here.
Right.
And I guess the second thing about it, that I know this seems counterintuitive for you, because why can you still access the numbers after you free them? It's even worse than that, because even after I freed it, I can still go back and print out the numbers. Yeah, I can. As you can see, because it doesn't matter. You can access things that you have not claimed. And we already showed that previously with these weird random numbers getting printed out that don't belong to you. So now that you freed it, these numbers, this space no longer belongs to you, but you can still access it.
Okay. So the only difference is maybe it's ready for allocation.
Exactly.
For other parts of
Yeah, exactly.
But this thing is still there.
It's not safe at all. Basically, there's a system, but there's no safeguards around the system.
Okay.
Yeah, that's how it works. It's a little weird. It feels very low level, and it feels like you can hurt yourself really easily, right?
Yeah.
Yeah.
Exactly.
That's how C programming is. And when you're doing C programming, you need to be careful, and you need to like double check things, make sure you got things right yourself.
Yeah, but I believe it's pretty useful for like you all have limited memory, like a little machine that makes a robot or whatever, like really small, and then you only have this much memory to work with, and then you have to do something like that.
Mm-hmm. I think this is a good stopping point. Perhaps later we can talk about the automatic memory management schemes.